Congratulations, Achintya. You're already, I think, sitting, on beach. Looks like. So, Professor Achintya Kumar Dutta has done his MSc and from Vishwabharati Shantiniketan in 2009, and he obtained his PhD from NCL Pune in 2014, and after that he did a postdoc in one of the Max Planck Institutes in Germany, Max Planck Institute for Chemical Energy Conversion. Then he joined our department in 2017 onwards, and maybe all of you might have noticed, couple of days back, mail is circulated by Dean FA that he has obtained the Nasi Young Scientist Platinum Jubilee Award. Congratulations once again for that. And with this brief introduction, I request Professor Achintya to deliver his talk.
So the topic of my today's talk is excited state quantum chemistry in the presence of an environment. I'm an assistant professor in the Department of Chemistry at IIT Bombay, and my primary research area is development of quantum chemical methods for excited states. I use the concept of effective Hamiltonian and localized orbital for that purpose. I use this developed method to study electron attachment induced radiation damage in genetic materials, and a big part of my research goes into development of an Indian quantum chemistry software package Bagh, the first of its kind. So I'm going to cover all these three topics very briefly. By training, I'm a quantum chemist. So quantum chemistry involves the application of the laws of quantum mechanics into the chemistry. And if you solve Schrodinger equation, the psi contains all the information about the molecule. Problem is that Schrodinger equation cannot be solved exactly beyond model systems, so one need to go for approximations, and the approximations available for solving Schrodinger equation for atoms and molecules can be categorized into two broad categories. One is wave function based approximation, they are accurate but costly, and the other way where you write the energy as a function of density. They are popular because they are efficient, but there is no systematic way to improve density functional theory, and if you are interested in excited state, it can be quite error prone. So wave function based methods has an advantage over DFT on terms of accuracy. So if we can increase the efficiency of wave function based methods, it can broaden its horizon of applicability, and that's where I work on. Of course, one obvious way to increase efficiency is go to for supercomputers and write massively parallel programs which scales over thousands of processors. But to us, that's a brute force approach of doing things. What we want to do is that we want to rewrite the equations in such a way so the sparsity inherent in the wave function automatically comes out of it. And for that, we use the concept of effective Hamiltonian. So what is an effective Hamiltonian? An effective Hamiltonian is a Hamiltonian that acts in a reduced space and only describes a part of the eigenvalue spectrum of the true Hamiltonian. Suppose this is the eigenvalue spectrum of the true Hamiltonian. What effective Hamiltonian does is that it extracts only a subpart of it, which we call P space or a principal space, and rest of the eigenvalues belongs to the Q space or the complementary space. Now, how can I guarantee that the effective Hamiltonian has identical eigenvalues with the original Hamiltonian? So we describe the effective Hamiltonian as a similarity transformation of the original Hamiltonian, and the mathematics of similarity transformation guarantees that the matrix elements of the effective Hamiltonian has same eigenvalue as the original Hamiltonian. And we choose the U in such a way that the coupling between the P and Q space vanishes. So I can now get eigenvalues for this small space just by diagonalizing this small Hamiltonian instead of diagonalizing the original big Hamiltonian. The concept of effective Hamiltonian is quite popular in chemistry and has seen multiple applications in gas phase. But real life chemistry happens in the presence of an environment. That means we need to consider the effect of environment in the quantum chemical calculation. One easy way is to treat the environment as a polarizable continuum. If you have a molecule in a solvent, you can do that. But more elegant way to treat the environment explicitly. Of course, treating the entire environment using Schrodinger equation is out of the question. So one need to go for multi-scale model. And one of the most popular multi-scale model is a QMMM approach, where you take the molecule, you fragment them in two parts, where the chemically important part you treat them in quantum mechanics, rest of the part you treat in molecular mechanics, and that's you do the calculation on them separately. Now this yellow region denotes the boundary between the QM and MM, and you have to treat them very carefully. So what is generally done, you fragment the bond passing through the boundaries, you cut them, and then you put hydrogens to saturate the dangling bond, satisfy valency, and then do the calculations. It's very popular. Almost all quantum chemistry software packages has this approach because it's very easy to implement. Problem is that the moment you cut bonds, it's no longer your original system. Secondly, the electron densities cannot interact through these cut bonds. So if you are dealing with excited state, then it's quite problematic. We use an alternative approach for that purpose. We know the canonical molecular orbital, the standard molecular orbital we read in undergrad chemistry, they are delocalized. But one can do an entry transformation to reach into localized molecular orbital, which is localized into a small part of the molecule. And by using this concept of localized molecular orbital, you can fragment your entire system into small fragments. Here, different color denotes different fragment. Just to note here, this fragment means the orbital is localized only in that part. There is no explicit cutting of bonds. So this approach is different from the previous link atom approach. Now we bring the concept of effective Hamiltonian here, and we construct the effective Hamiltonian for the entire molecule. However, these amplitudes corresponding to these U operators are obtained in an approximate way. So if I want to represent it schematically, so where 1 is my active site and 2, 3, 4 is my environment, and this is one of the representative term in my calculation of U amplitude, where x and y denotes the location of the orbitals. Now the advantage in quantum chemistry is that electron always correlate in a pairwise manner, 2 electrons at a time. So by looking at where these electrons are localized, I can make sure that I treat different location of x and y differently. So if both of them are localized on my active site, then I treat them very accurately. If one of them is localized on the active site and the other is on the environment, then I treat them approximately. And if both of them are localized on the environment, I just neglect them. So by using this approach, I can drop terms from my equations without even doing any fragmentation. Because the effective Hamiltonian is constructed for the whole space, it allows mutual relaxation of the active site and the environment. Of course, derivation of the equations and writing them in form of computational program becomes much more involved. But because of the accuracy and efficiency it offers, it's worth to take that pain. And currently it's available for excited, ionized and electron attached states. So we developed this for last 3.5 years during my stay in IIT Bombay. Now, one of the main reason of development of these methods were that we were interested to study radiation damage to genetic materials. We know high energy radiation causes damage to our genetic materials, and understanding its mechanism is one of the important biological problems because it has implications both in the cause and the cure of cancer. Now, the radiation damage can be two ways. One is a direct damage where high energy radiation knocks out electron from the DNA directly. And the other way is that because our DNA is surrounded by a lot of water, so the radiation knocks out electron from the water, and then this extra electron get attached to the DNA, and that leads to damage. So we are more interested in study the indirect effect, which is called a secondary damage, and the secondary damage pathways are traditionally interpreted in terms of quasi-bound or resonant states of the anion, whereas we want to describe in terms of bound anionic states. So DNA basis has two kind of anion state. One is a dipole bound, where the extra electron is away from the nuclear framework but and attached by a charged dipole interaction, and one is a traditional valence bound orbital, where this extra electron is attached to the antibonding orbital. Now the dipole bounds alliance are generally very less studied in the literature because you require specially constructed basis function to study this kind of states, and they are not available in a CAN software package. So one of our first work from IIT Bombay is to develop these basis sets. Now this dipole bound state is vertically bound, and the valence bound state is so when it's in neutral geometry, the dipole bound state is the only bound state, and as the geometry get distorted due to formation of an ion, it's get converted to a valence bound state. That means the dipole bound state captures the electron and then passes through the valence bound state. Now the transition between dipole bound and valence bound state is optically forbidden. So now question is how this transition then happens. So molecular vibration can cause transition between the two, and to understand how the transition actually happens, we calculated a linear transit between a dipole bound and a valence bound geometry. So I start from a dipole bound, I go to the valence bound, and lambda is a linear transit parameter. So if lambda is 0, then it's dipole bound. If lambda is 1, then it's valence bound, and we have the intermediate geometries. Now, as we do the transition, we see there is an avoided crossing in the potential energy surface, and that means two energy surfaces comes very close, and the bond Oppenheimer approximation breaks down here. And this is a problem if the Born-Oppenheimer approximation breaks down here, that means we cannot treat them in terms of bound state quantum chemistry. We need to go for something called a diabatic basis. And we call this doorway mechanism because it's the dipole bound state which captures the electron and acts as a doorway. So it's like through the doorway that electron enters and then gets converted into a valence bound state. Now this is gas phase molecules, but real life quantum chemistry happens in the presence of environment. And for a theoretician, we are very much comfortable with model system because it helps us to see a lot of things. So we started with a very simple model, uracil and a single water molecule, and then we tried to calculate the transition between the two. Of course, it's a model system, nothing to do with real life, and we found that there is a similar avoided crossing mechanism operating here, and you can treat them using diabatic surfaces. Now, to understand how it happens in a bulk solvation, so what we did, we put a nucleobase in a bulk water box and then did QMM simulation. So when we started the simulation, we see there is only one bound state where the electron is localized on water, like a dipole bound state. As the simulation progresses, we see a second anionic state arises, which is an excited state, and there the electron is localized on the nucleobase. As the simulation progresses further, the nucleobase bound state becomes the ground state and the water bound state becomes the excited state of the anion. So, and from the experiment, it was already known that the excited state of the anion plays a crucial role in the electron attachment process. So, one can describe the entire phenomena like a doorway mechanism where the water bound state, where the electron is localized on water, they act as a doorway for electron capture. And then through the mixing of electronic and nuclear degrees of freedom, the electron get transferred to a nucleobase bind state, which finally is where the electron is localized on the nucleobase. We also calculated the rate of electron transfer, and we found it to happen in a picosecond time scale, which is consistent with the available experiment rate. This is of course for all one nucleobase, but what we see that similar mechanism is also observed for the other nucleobases, and we show that the doorway mechanism is a general mechanism in principle. And recently we have demonstrated that this doorway mechanism can also explain electron attachment induced DNA strand breaks, and it can properly reproduce the experimentally observed fragmentation product with a sufficient accuracy. So the doorway mechanism sounds like one of the alternative pathways of radiation damage. Of course, the model system we are using is very preliminary and it has nothing to do with real life. So we are expecting it to go to much better model system, bigger molecules with proteins, and understand what things are happening in there. As I told in the beginning, one of my main research areas is the development of an Indian quantum chemistry software package, and we have developed this quantum chemistry software package Bagh, named after, of course, the queen of IIT Bombay campus, our famed leopard. This is the first general purpose quantum chemistry software package to come out of India. Now, in the development of a new software package, one need to write millions of lines of code. They are time consuming and it can be error prone. So it's always easier to use a automatic code generator where you can feed the expression and it will automatically generate efficient programs. Now, this writing of code generator is not an interesting problem for a person who is working in chemistry. So chemistry student generally does not get interested in this kind of work. But one of the advantages of being in IIT Bombay is that we get computer science students. So I get this computer science BS2 second year BS student Arpan Basu is very bright, and he came to me as a summer student, and during last summer in 2 months he has written a code generator which can accurately generate efficient program out of mathematical expression. So that actually really speed up our development of this software package. And Bagh can perform accurate wave function based calculations using Schrodinger and Dirac equation. One of the strong point of this new, now question may come, why I'm developing a new one? So one of the strong point of Bagh is that it has natural orbital based methods. So natural orbital can reduce the computation cost of ground and excited state calculation without sacrificing a lot of accuracy. And then this method becomes competitive to a DFT functional theory, keeping intact its systematically improvable nature. And if we come into terms of comparing with commercial software packages, currently Bagh is the only software package that features natural spinors for relativistic calculation. So when it comes to doing relativistic quantum chemistry, Bagh is the fastest, and it also allows direct integration of machine learning models, which are not available currently with any commercial quantum chemistry software package. Of course, the Bagh has to go a long way in terms of development of new features, writing efficient programs, and making it much more user friendly before it can compete with commercially available software packages, but we are going into that direction. In the end, I want to thank my student who actually did all the hard work. Because of the lockdown and the physical distancing, I cannot keep all the people together. So the group picture actually contains only a part of the student, rest of them are here. I want to thank my colleagues at Department Chemistry for the help, and IRCC IIT Bombay for giving me this opportunity to speak here. Of course, the funding agencies, DST Inspire, ACRB, CSR, HRDG, and IRCC for generous funding. Thank you very much for your kind attention.